So what is dry on a gin or on a champagne? That's pretty strange. On the other hand side, drying of UV inks, it's definitely a curing process, as we have heard several times, but unfortunately called several times as drying. In a hybrid ink, we might see partially something which is dried, but here it's only the evaporation of the water and the solvent. It's much more drying required than just evaporating the water. And finally, thermal curable powders, which are typically called with dry powders. A powder is dry from the very beginning. If it's wet already, it's a slurry, and that again needs something different. So the definition of drying is something which is pretty much individual, but can be concluded already that there is no proper quantified physical parameter for dryness or drying. And that's why we talk about the next step when the ink drops have reached the surface, how it's proceeded the process of getting it finally fixed. We have to separate two different kind of substrate types. One is the porous type, which can absorb, which can allow penetration of a liquid phase through the system. On the other hand side, we have fully covered, shielded surfaces, substrates, and we are not only talking about graphical applications. This could be metal, this could be glass. So therefore, the two types have to be separated. And what we have heard already from the very first presentation this morning, the ink generation, the drop generation is done in microseconds. The reaching on the surface and their further spreading is also taking place in a very short time, definitively more or less in the range of less than a second. In some very specific prepared pre-treated substrate, it might come up to 2 seconds. But everything else above this time is getting the more or less a stable setting of the ink, and you cannot adjust anything on the formulation of the ink droplet afterwards. And therefore, the treatment of this applied ink drop in this first period is essential for the further print application and the further pronunciation of the printing quality, since we have to take into account that with penetrating papers, for example, we have the swelling of fibers. The same would be given at wooden-based materials, so that the water reaction would give us a fiber swelling and the breaking of the interfiber bonds, which is strongly already damaging the substrate, which is the reason why today, still in the graphical industry, a lot of problems are, or let's say, a strong limitation limit, low limitation limit is given for flat printed products. Even the well-known good print quality is far away from the achievable flat products you have with offset printing. This can be overcome if you are able to set the ink in the very first time before you have really the opportunity to penetrate inside of the substrate, and that is essential that you avoid the penetration inside of the substrate. On the other hand side, if you have a non-porous material, intercolor bleeding is something which is well known. So therefore, the fixation before the colors are running into each other is also crucial for print quality. And all that shows you that the drying technology is really driving all these aspects. And before we come to that, I think I would like to do some principal data we need for the applications. Number one is, you see here an absorption diagram of the amount over the wavelength for dye-based inks. And what you can see is, in the optical area, sure, there is a difference between the different colors, CMYK, but above the visible light, above the visible spectrum, all these colors remain with the same absorption, different in the different wavelength range, but identical, which means each of the color will absorb the same energy with a given wavelength. This is only different in the optical area, and more or less the same also in the UV area. That's dye-based inks. Pigment-based inks look a little bit different. They show, again, in the visible light, their different behavior due to the color. They are pretty similar in the UV area, but in the non-visible IR area, there is still a slight difference between the different colors. And in the longer wave, these colors remain on the same level, but the black pigmented ink is still high, independent of the wavelength range. That's an important effect, which we will see that a lot of people are seeing, that it might be advantageous to run in the longer wave IR for drying purposes. Is that true? Shows the next picture. And that is the absorption characteristics of different papers. You see 60 grams, 115, and 260 grams. Again, absorption over the wavelength. Again, the UV area, certain high absorption. Then you see the visible and the NIR area. And again, the longer wave IR, which shows that the paper has a very high absorption in the longer wave IR, which is, if you compare that if you compare that now with inks, which is shown in this graph. In this graph, that the absorption of the substrates are higher than the absorption of the inks. Just for clarification, I also wanted to show other coatings like PDOT or the Flexo ink on graphene. There's a very low absorption in the NIR, a very high absorption in all areas, but the substrate is very low. That's why we can run these on temperature-sensitive materials. Now, coming to the different dryer technologies which are taken into consideration today: hot airs, drum dryers. If we talk about IR, most of the time we talk about mid-wave IR in combination with hot air. And then we have the other group of NIR, which is developed by us specifically with integrated high airflow air and warm impingement integration into the process tunnel. To summarize a little bit these technologies, I think it is easy. The hot air requires an airstream on the top of the ink film and the surface of the paper, because it doesn't separate between the paper and the printed area. And we have heat conduction onto the substrate, and due to the high temperature, we get out the water and or the solvent, and get a solidification of the printed area. But we have to take into account that this takes a long time due to the low energy density and due to the accepted lower airspeed we can run. There is a strong time due to the increasing of the temperature that the viscosity drop of the still liquid film comes down. So you have in the first area of this drying process a stronger penetration inside of your substrate. And at the end of the day, the drying process is only completed if the energy has been provided to heat up the substrate mass, and the very little part of evaporation of the water is a minor part of this process. So at the end of the day, the substrate temperature is as hot as the printed pattern, and takes a long time and dries out papers which have a certain amount of water involved. If we go to a hot plate process, we even have a situation that we are not applying the energy to the printed side. We take it from the back side. It's an iron principle. So we heat up the back side and get the heat through the heated surface, the substrate, and then by heat conduction through the backside of the paper heats up and gets the printed area as well, sometimes heated up and evaporates. Here, the full mass is a must to heat up. Number one. Number two, in order to get a heat conduction flow, you need a higher temperature in the substrate than in the ink. Otherwise, you wouldn't have a heat flow. And number three, since you have maybe a higher, thicker material, it takes a long time in order to get the energy through. And finally, if you are not applying a proper airflow and air ventilation in the system, which most of the solutions which have been on the market till now have been given, there is a very catastrophic energy balance to that. The right now introduced newer systems have understood that air ventilation is important, so therefore they have improved a little bit their systems now. But again, energy is fully the energy of heat up the mass of the substrate, and then finally a little bit the energy for the evaporation of the liquid phase, water or the solvent. Coming to the IR, and here mainly driven to the mid-wave IR, which is the most pronounced areas, but there is no strong difference because the energy is absorbed again on the surface of the substrate due to the shown absorption characteristics of papers compared to the ink. So the printed pattern, and that is, you see, I like this photograph because it's yellow, magenta, blue, and black. So the YMCK. And if you now address this to a mid-wave IR system, it will look like that. There is no difference in the contrast between the paper absorption data and the ink beside black. And that's how your printed pattern is seeing the energy. And that means if you now assume that these printed patterns are wet, so there's more energy needed for that, the time which drives to get everything dried is that the non-printed areas are fully over-dried before the wet ink is finally fully dried. And that is why you find out in hot air dryers and mid-wave IR dryers that your remaining ambient moisture content in your substrate is 2%, maybe 2.5%, while the typical environmental moisture is 5 to 5.5%, and that changes significantly the quality of your printed product. And it is totally wavy as you see it. On the other hand side, again, the energy is absorbed, yes, at the surface, but in order to get that too, again, heat up the full mass and then get the water evaporated. And now we talk about the NIR. What is the ineffective way of not absorbing the energy in the substrate and a lower absorption in the ink, except the black? And that is because we are penetrating inside of the coating, and because we are, in this case, even going through the substrate, we have to put in a proper reflective area so we get a multi-reflection, and the ink is absorbing mainly the energy, and therefore if we apply sufficient energy density, the ink is dried more or less instantaneously. We can build a very small dryer. We can reduce the drying time to a minimum down to tenths of a second or even below. This allows us to apply the drying unit immediately in between the inkjet nozzles because it requires so little space, or apply it immediately after the inkjet, so the time before it's entering the dryer is also minimized to a very short time. And that all allows us to adapt more or less the drying energy to the printed pattern. And this allows us to have a very low temperature in the substrate. And this allows us that most of the energy which is required to get it properly dried is resulting only from the energy which is required to evaporate. Sure, we do not have 100% efficiency due to the differences in the absorption characteristics, and there is a heating up due to the heat conduction into the substrate. And having said this, a very thick paper has a certain requirement that at the boundary layer between the printed pattern and the substrate, we need a certain temperature to get proper adhesion. So therefore, we will not have a process finished on totally untreated substrate. So there is a certain amount of energy introduced into the substrate, but significant less. And that's the reason why we come to this specific advantages. Number one, because we can do it instantaneously, we can fix immediately the ink droplet when it achieves the surface and arrives at drying or pinning unit. We avoid mostly the penetration. This avoidance of penetration gives us the avoidance of swelling of the fibers on the one hand side. This gives us also the avoidance that the water penetrates into the substrate, which requires more energy to get the water out again, due to the fact that due to this penetration process, the porosity configuration is also changing while the water is absorbed in the substrate. That is important as well. All the other techniques, let's say it this way, none of the bespoken techniques allow us to evaporate the glycols, which are necessary for all the today's DOD inkjet systems. But now, why can an IR remove the glycol, since we are also not achieving the temperature which evaporates the glycol? Pretty simple effect. You do it instantaneously, very, very fast. And now you look at your pan at home when you fry a steak or whatever, and you make it very, very fast. All the grease is coming out and sprinkling around your plate, and it is absorbing the water which is evaporating, and this water has a mechanical fixation with the grease, and that's what is taken out. And the same we are doing when we are drying very fast these ink droplets. We disrupt some of the glycol out of the system. I mean, this only can be done until the status that we would really destroy the printed pattern. I can easily say we have not achieved that, because the energy density you would require for that is much higher than that we can apply. So we achieve a certain disruption of this glycol, but we cannot really do this on a total full amount, but allows us to increase the application range to much, much broader paper or substrate qualities which otherwise are not able to apply. Then the low stress I have said, and specifically the applicable substrates of really thermal papers. Now some applications. Here, blue is before, red is with the adphosNIR technology. You see, the point is in all cases the same. We can run higher speeds. We can run fully coated materials with a full speed. And, the other way around. We can do We can do blue is adphosNIR and red is the former way. Sorry for that. Otherwise, it would be, I think, not very addressable. So we can run the full machine speed, uncoated as well as coated. What is important, the energy is half compared to the mid-wave IR system. And this is something I can conclude for all the applications we have resumed in the market. It is half to 1/3, down to 1/3 of the energy we require when we are comparing this with hot drums, hot air, IR, combination with hot air. So there is a huge advantage of energy saving. I'm a nuclear engineer, and I would say energy is nice, but it's still too cheap today. So therefore, it is a nice marketing tool to talk about energy saving, but it's not really driving the operation cost. I think the much more important thing is we get flat products. The first time we have proven customers, they say we never saw a flat product which looks like an offset quality print, and that is what we feel is the advantage, that you are saving money due to the fact that you get a better product and you get better production due to the requirement you don't need remoisturing, you don't have the problem of keep the systems a day or 2 days before you can finally finish it, because the glycol has to be somehow penetrate into the substrate. It can be immediately finished in one step, and at the end of the day, there is a significant saving in space. Here is an application which couldn't be applied physically with an alternative dryer. That's corrugated boards. The system shows a scheme because it's still under beta application and will be shown at Drupa next year. But you see the pre-coating with the drying, you see the process color inkjet with the drying, and there's even a post-coat in there. You see the data, 200 meters, the width, and the total drying length for the inkjet. And that is the reason why we can apply that, because we keep the very low temperature on the corrugated board. And if you have a temperature difference in your corrugated board, especially if you are talking about bigger corrugated boards, and they can be as big as 10 centimeters, you will have the banana, which I think is something you have to avoid if you want to take this as a display in the supermarket. And on the other hand side, again, as I said, there is a significant energy saving due to the fact that we do not have to heat up the full mass of the substrate. And the only alternative you would have here is run an air dryer at a low temperature, but that requires, at these data, a very, very long press. That it's not limited only to graphical applications. I took this one. This is a flooring application, very wide width, lower speed, but also CMYK with interstation drying required. Why? Not because we cannot dry it afterwards. The problem is intercolor bleeding. To avoid that the colors are running into each other, we have to dry them in between before it's applied. You see the materials. You see what type of thermal heat stress is allowed on the system. With these data, there is not too many thoughts about what alternative could be used if we are not going for pure UV application, which was the past former solution. That is the last one. I wanted to show at my application examples, and this is the additive manufacturing, so-called 3D. And here you see a typical range of speed we could do with. We can apply this on plastics and metals. Metals is a challenge today due to the high melting temperatures. And the big advantage of the NIR is that because of the high energy density, we don't have to have this preheating level as close as possible to the melting point, due to the fact that we can have a higher delta T overcome with a very high energy density to the melting point. We can preheat, for example, plastics just above the crystallization point. We could do it on air, on ambient, but then we would have a deformation due to the crystallization change of the material. On metals, we do this from ambient, and the other advantage is this instantaneous melting allows us also to avoid the heat conduction into the structure, which gives us smoother surfaces, and the adjustable heating size allows us again to a strong reduction in energy. But that's something which is still in the R&D phase and first prototyping. Coming to my end, and that is unusual that I'm in time. The drying process is starting immediately as soon as a droplet is touching the surface. And that's something important. The old thinking, the former thinking of leave the system as much as possible and give the penetration capability because we need less drying. It might be nice for the ink company because they sell more ink, because more ink is penetrated inside. To get the same color density, you need significant more ink. But that's the one thing. The other thing is you cannot expect that your printing quality can be as good as if you would do it immediately after the droplet has been reached the surface. The drying technology, as I showed, is therefore significantly influencing besides the quality, the performance, and in a lot of application even is driving the answer of, can we do it with inkjet or we can't do it with inkjet? If you want to do DOD inkjet on plastic materials, there is a very little working space today outside of applying the NIR technology due to the thermal stress which is coming around. Energy saving is a significant point, but the costs which are driven are the printing process costs, which is more or less the arrangement of the printing device as well as the whole configuration. Substrate costs, due to the fact that you can apply this on a much wider range of non-specifically inkjet pre-treated materials. That saves a lot of energy. We have a customer in the UK. He saves £200 per ton of paper, which is a payback of the system in less than half a year. So that also gives you a certain, it's not tiny data, it's really big numbers. And at the end of the day, the overall process of the system is influenced by how you are doing it. I hope I could give you a little bit an introduction of it. In our booth, we show it a little bit noisy because the equipment requires a good air ventilation. We show the difference of NIR compared to IR, and it shows what is the difference in thermal heat to plastic materials, to heat-sensitive materials on water-based, fully 100% water-based commercial ink. Thank you for your attention, and sorry again that my colleague has not given you this presentation. Hopefully it was still a little bit clear to you. Thank you.
Thank you, Mr. Bahr, for your nice contribution. Are there questions from the audience? There's time for 1 or 2 questions.
Is all this applicable to textile drying? I suppose cotton and paper are just about the same nature, but is it applicable also to polyester and other type of textile?
That's a good comment. I would have liked to give you already some stronger experience data on textile. We have done some preliminary trials in the lab, and it clearly shows that we can apply it as well on for the inks which are used for textile materials. The problem is that we have not yet really quantitative data on that, since we have only started this several months ago. But I would say the likelihood to get this answered in the same way as we have the experience today is almost 1. Yeah?
Okay, maybe a last question from my side. How strong is this already introduced on industrial level, your technique?
Okay. All what I've showed here, and except what I just mentioned, is it is not something is on the lab level, on the technicum level. It is widely proven in the market. I think on inkjet systems, water-based systems alone, we have within the last 15 years more than 1,000 applications commercially in the market. It started even 20 years ago with Cytex technology when we tried water-based inkjet printing on thermal paper. That was the production of the thermal print tickets from the German railway station. There we have tried the codes, the barcodes, and the numbering. But beside several hundred mailer bases, there are all high-performance hybrid applications, more or less 90% out of them, which are given up to 1,000 meters per minute, which are internationally in the market, are based on adphosNIR driers. The DoD application and the digital printing applications in the last years are now in the range of 100.
Okay. Thank you for your answer. Thank you again.
Thank you again. And this is just for you to see. This could be a device for interstation pinning on a moving flatbed system. This is as small as a LED system, sure, but you can apply here speeds double as high as with a UV pinning system. Thank you.